Welcome to the 8th lecture of graph theory. In the last class we were discussing the problem of covering a directed graph with a collection of directed paths. So here this time we are given a directed graph. That means there are edges and each edge has a direction. Now these are the directed graphs. So now we want to find out a collection of paths such that every vertex belongs to exactly one path. That means this path should be disjoint and also it should cover all the vertices. Here for instance, for this graph I can select this path and say this path. This two directed path will cover all the vertices of this graph. So this kind of paths are called a path cover. For instance, we can look here. A path cover of a directed graph G is a set of disjoint paths in G which together contain all the vertices of G. So now we are going to prove the Gallai Milgram theorem, and before that, so let's state the theorem like this. So suppose we are interested to find the minimum number of paths that can cover a directed graph in this way. That means we want a path cover of minimum cardinality. We are interested in the cardinality of the minimum path cover. We will call this parameter say minimum directed path cover of G, and we are interested in the cardinality of this. So we may not always write like this. We may abuse the notation and say MPDC of G to represent the path cover as well as its cardinality which achieves the minimum. And now to find out the minimum path cover, so this is the question. Now this parameter always is upper bound by BDC of G is at most alpha of G is what we are going to prove. This is called Galle Milgram theorem. So slightly stronger statement we will prove here. Alpha of G is the independent set. Remember, the independent set of a directed graph is the same as the independent set of the underlying undirected graph. So there is no difference between that. The direction will not make any difference in the independent sets. But path cover can be different in a directed graph and an undirected graph. For instance, you are given a directed graph and you find a path cover of that. You have to cover the vertices of the graph with directed paths. The path should be disjoint and each vertex should be present in exactly one path. So should be present in some of these paths. That means all the vertices should be covered. But now if you remove the directions on the edges and look at the underlying undirected graph and look for the minimum path cover, you may be able to cover with smaller number of paths. For instance, you can easily see this example. See, let us take this simple example. So here suppose this is my directed graph. If I am asking for a minimum cardinality path cover here, so I can clearly say that minimum path cover, minimum directed path cover of this graph is equal to 2, because so once you take, see, you may take this one, because you cannot go further. Only in any path, any directed path you can get only 2 vertices, because the arrows doesn't allow you to go further here. Now you will have to take another one singleton path, right. So this and this will be the 2. But on the other hand, the underlying undirected graph will look like this, because if you remove the directions on the edges, to look like this. What will be minimum path cover of G? That means this D denoted the directed graph. So this is only 1. So it can be different in both cases. Of course, this is smaller because any directed path cover, when you remove the edges, will give you a path cover in the corresponding undirected graph. But the other way is not true. For instance, a path cover in the underlying undirected graph may not convert to a directed path cover. Yes, so what we wanted to prove, as I wrote here, this is what I want. For given a directed graph, the cardinality of the minimum MDPC directed path cover is less than equal to alpha of G is what I wanted to show. Suppose I look at the question. So just to understand this question, we may look at the undirected version of this thing. So given a undirected graph G, so I am interested to prove, say, is this true? Minimum path cover of G is always less than equal to alpha of G. This is what the question is in the undirected version. So as I mentioned in the last class, this is a very easy question because you can always take a path cover. Say you take a minimum path cover. Suppose this is a minimum path cover of the given graph. So these are disjoint paths, and then you pick up the n vertices of this path cover. They should always form a independent set in G. Why? Because otherwise, suppose if there is an edge here, suppose you had an edge here, now you can, of course, this is a I could have replaced these two paths with this one path, isn't it? So therefore we would have got a smaller path cover, and which is not possible because we assume that we have already taken a minimum path cover. So you can see that in this undirected case, not only that we have got an independent set of cardinality, at least the cardinality of the minimum path cover, that independent set was such that the n vertices, this independent set actually is the n vertices of the paths. That means I selected one n vertex from each path. That is what the independent set was. So will the same trick work in the directed case also? But it doesn't work. Why doesn't it work? Suppose this is the path cover of the directed case. So this may be the directions. Now let us try to pick up the n vertices, like say this is A, B, C, D. These 4 n vertices let me consider. Should they always form an independent set? Not necessarily. We can have some edge like this, because the direction may be like this. In that case, we may try to follow this, try to construct a bigger path, but it will go here and then it will not be able to move further because the arrows are in the wrong direction. You cannot take, unlike the earlier case, we cannot continue like this. So we still will have 2 paths. Of course, you will cut here and then you will get a slightly longer path here, but slightly shorter path here. That is all. So, but the cardinality will remain same, there will not be any contradiction. So, there is no guarantee that you will not have edges of this sort. So, therefore, that strategy is not true here. So, of course, so one should ask whether this theorem itself is a very reasonable one, because in the undirected case it is true, but given an undirected graph, you can make several directed graphs from that. For instance, every edge can be, so given an undirected graph. So this is, see here, if I for instance, if I take this undirected graph, Of course, there are several possible ways of orienting the edges. So, this can be oriented this way or the other way, this way. So, therefore, there are two ways of orienting each edge. So, there are 2 to the power number of edges ways of orienting it. So, there are several directed graphs which can be formed from an undirected. Some of them may be same, but as far as we are concerned, we can get several directed graphs from one undirected graph. So, what if even one of them violate the theorem? You should understand that alpha independent set, the biggest independent set will not change by giving some direction to the edges, that will remain same, while the path cover cardinality may drastically increase. So, let us take one example. For instance, this is a very easy example that comes to our mind. So, this is a path, right. So, here 1, 2, 3, 4, 5, 6, 7, let us take 8 vertices. So, we know that the in the undirected case, minimum path cover cardinality is equal to 1 here, because there is just one path, that is enough, and of course, alpha of g is equal to 4, right. So, let us say n by 2 if n is the number of vertices. So, here this vertex, this vertex, this vertex, like that we can pick up, right. Now, suppose I direct the edges this way. First I directed it this way, that means this is like this, then I directed this edge in the opposite direction, and then I direct it this way, and then I direct this one this way. So, this one this way, this one this way. So, in the wrong direction, the opposite directions, I from each vertex will see two arrows going out or 2 arrows coming in. Here it is coming in, 2 arrows. So, it means that if I try to take a path, I start from anywhere, I will have to stop. If I start from here, I will have to stop with the next vertex. I will not be able to go further. If I start from here, I will have to stop here. If I start from here, I will have to stop here or here. So, there is no way of getting a path containing more than 2 vertices in it. That is the way we have. This way we have increased the cardinality of the minimum path cover so much, because now a path can only cover 2 vertices at most, and by 2 as is the MDPC, right. So, MDPC of G has become n by 2, right. So, this is one path, this is another path, this is another path, this is another path, right, like that. This is the only way we can cover it, but alpha remains same. So, it has reached here, but still it is less than equal to alpha of g, interestingly. But look, the way we have oriented the edges, the cardinality of the minimum directed path cover has gone up to n by 2 and it touched the alpha. So, this is only a simple example. Is it possible that I can have some complicated examples such that it may cross alpha? So, maybe the theorem itself may not be true, that comes to our mind. So, then thinking like that, another example which will come easily to our mind is the complete graph Kn. So, what is so interesting about Kn? The Kn, the independent set is the maximum independent set cardinality is only 1. You cannot have an independent set of cardinality 2 or more. So, alpha of Kn is equal to 1. So, why? Because now any so, of course, in Kn there is a Hamiltonian path. What is a Hamiltonian path? That means a Hamiltonian path is a path which touches or which visits each vertex once and only once. So, this is one term which we should be familiar. Hamiltonian path means it will go from vertex to path will move from vertex to vertex and every vertex will come exactly once. Every vertex will come and only once. The Hamiltonian cycle means, so it is a cycle the same way, every vertex will be present in the cycle exactly a cycle. So, a cycle which goes through all the vertices, but exactly once. This will be Hamiltonian cycle. Now, we know that in a complete graph, any sequence of vertices, if I take 1, 2, 3, 4 up to n, and if you traverse the edges, you will get a Hamiltonian path. Therefore, that is no big deal in undirected Kn. But what if I try to orient the edges of Kn in such a way that, see, my intention is to somehow beat this. That means to show that I can get an orientation such that the minimum path cover cardinality increases to more than 1, 2 at least. Or in other words, I will somehow try to orient the edges in such a way that there is no Hamiltonian directed path in after orienting the edges. Is it possible? For instance, you may want to try orienting a triangle. So, but unfortunately, whatever way you triangle, you will orient your triangle, you will end up with a Hamiltonian this way or this way, whatever Hamiltonian path here. But the triangle is quite small. You can take a K4 and try. It will be interesting to see whether K4 or K5. Interesting to see whether you can give direction to the edges of this graphs in such a way that there is no Hamiltonian directed path in these things. But so it's after some attempts, you may realize that, so you can always get whatever way you orient the edges, you end up getting one Hamiltonian path, sorry, directed path. So, for instance, I can give a quick proof for that. For instance, so let's try with 2. It's very easy to prove. K equal to n equal to 2, K2 has of course, irrespective of the orientation, you will have a Hamiltonian directed path. Similarly, Kn, K1, K3 if you take, it's very easy to show. So, let's say up to Kn minus 1, we have shown that irrespective of the way we orient the edges of the graph, so then we can end up with a directed Hamiltonian path. We can end up with a directed Hamiltonian path. So, it's so now how do I show that in Kn also, it is possible. So, we will take the last vertex, say this is the last vertex. You see, it is connected to all the vertices in this Kn minus 1. This is the Kn minus 1 and this is the last nth vertex. So, nth vertex, right. So, now see all this irrespective of you are giving some direction to this. Some of them may be directed like this, some of them may be directed like this, whatever it is. So, there will be some directions. What you do is, here you will try to find, because by induction you know that there is a directed path here, maybe some directed path is there here, right, like the directions are like this, right. Now the idea is, so you will first look here the last vertex of this directed Hamiltonian path in this thing and see how this edge is oriented. If it is oriented backward, that means then we are done, because if it is like this, then we are done, because we can just attach that vertex to it, you get Hamiltonian path. So, it should be oriented like this. Now, we know that so if all the edges are oriented like this, right. So, if all the this in the end this also will be oriented like this. So, then I would start like this and complete the directed path. So, therefore, if I keep going like this, just checking the orientation from this vertex to the edges, going back in this path like this, you will see the orientation changing once, right. So, at some point you will see that the path is like this. So, the path has orientation like this. At some point, say at this point, you will see that here the this is oriented like this. From here onwards, all the orientations are like this. Now, what will I do? I will rather I'll trace the path like that. I'll go come up to here and then go here, then go here, and then follow this, right? So then I can include it here. So this is one way of seeing it. You can try to get other proofs also. So therefore there is a Hamiltonian path in Kn minus 1 always. So therefore though initially it looks a little puzzling, so it is always there. So therefore in complete graphs also the theorem is true. Another thing we may want to check is the bipartite graph. So what will happen in a bipartite graph? So if you are given a bipartite graph, so these are the edges here, this is the undirected bipartite graph. Now if I want to make the cardinality of the minimum path cover as high as possible, the best strategy to orient the edges would be to orient all the edges from one side to the other, right? Why? Because you know, in bipartite graph, so if I trace a path, I will first go to the other side, then I will have to come back. That is the only way you can trace a path. Now you see that every edge is oriented from the A side to the B side. So once you reach the B side, there is no coming back to A side. So every directed path have to be of cardinality, I mean have to contain at most 2 vertices, 1 or 2 vertices, that is it. So now if you ask for this bipartite graph, what is the cardinality of the minimum directed path cover, we will immediately be able to say that that will be equal to the see the number of 2 length, that means length 2, that means the number of length 2 means number of vertices in the directed path is 2 paths plus the for the remaining vertices you have to just take singleton paths. So, but how many length how many paths can be there with exactly 2 vertices in it? So, you see there are edges and they are independent edges, they are directed of course from the A side to the B side, but clearly without some with some thought you can realize that it is essentially alpha dash of G. That means the biggest matching in G is to be considered, the biggest matching in G is to be considered, that is alpha dash of G, right. That will give you the maximum number of paths with 2 vertices in it. That is the only way we can take it. And for the remaining vertices, how many remaining vertices are? Total n are there, n minus 2 times alpha dash of G, because each edge has covered 2 of them. So, 2 times alpha dash is already covered, the remaining uncovered things are this much. So, you have to add that. So, this is the total cardinality of the minimum directed path cover of this graph if you orient a bipartite graph from the A side to the B side, every edge from. So, this will be n minus alpha dash of G, and by Koenig's theorem, you know, this alpha dash of G is essentially beta of G. And what is that? So, this one is essentially our alpha of G, isn't it? This one is alpha of G. N minus beta of G, we have already seen that alpha of G plus beta of G equal to n, then n minus beta of G is equal to alpha of G. So, it so happens that in any bipartite graph, this becomes this MPDC happens to be equal to, not just less than equal to, it is equal to this thing. So, somehow it is reaching the bound. If it is true, this theorem, Galle Milgram theorem, that that minimum directed path cover cardinality in a directed graph is at most its alpha is true, then in all bipartite graph they are tight, they are equality, isn't it? So, it is reaching there. So, therefore, so therefore, this is an interesting theorem. There are several cases where it is really touching the ceiling. So, let us try to prove it now. So, as I pointed out, we have seen that in the directed case we can get a collection of independent sets. So, in independent set in G such that it has a representative, this independent set has a representative set, representative vertex in each of the paths in the minimum path cardinality path cover. I am going to show that the same thing is true in the directed case also. Not only that we have an independent set of cardinality, at least the minimum cardinality path cover, cardinality of a path cover, but also that we will get one vertex of the independent set situated, placed on the paths, each path of the path cover. Earlier in the directed case we could take it as the terminal vertices, the n vertices of each path in the path cover, but in the directed case we may not be able to do that. So, I will have to take some internal vertices sometimes. So, let us see how we can do this thing. So, but we will be showing a little extra here, not just that if this P is a minimal path cover, this is what I am saying. Instead of minimum path cover, I will say if it is a minimal path cover, then there exists an independent set. Yes, such that for each P in P, S intersection P not equal to phi. So, we have some representatives from each path of the path cover in P. Therefore, the cardinality of S will be definitely greater than or equal to cardinality of my path cover, and definitely this is less than or equal to alpha of G. This is what I am going to show. But then what is this minimal path cover? So, we have seen other instances where we use this word minimal and maximal. For instance, we talked of minimal vertex cover. So, what was the minimal vertex cover? So, it is a vertex cover, yes, such that if you drop any vertex from S, say take an x element of S and consider S minus x, this will not be a vertex cover, not a vertex cover. So, irrespective of which x you take. So, that is the minimality of S, right, that is a minimal vertex cover. Similarly, we talked of maximal independent set, right, in the last class. Suppose some T is a maximal, not maximal, this is maximal independent set. What was the property? Then you take any y element of V of G minus T outside vertex and then try adding it to U. Then T union Y is not an independent set. This was the maximal independent set. So, similarly, we are familiar with this word. So, in the case of path cover, what should I mean by that? So, in the case of path cover, if I define it like this, it should be like P is a path cover, and I will have to say that it is a minimal path cover if I remove any P element of P is removed, then P minus this P, right, is not a path cover is what I should say. But then that is trivial, because any path cover, if you remove one path from that, it cannot cover all the vertices, because there were some vertices covered by that removed path, and now the remaining thing is not a path cover. So, in that sense every path cover will be a minimal path cover. So, that definition does not make sense. So, the minimal path cover is defined in a somewhat different way. So, we rather look at, suppose this is a path cover, I will just draw it like this. So, it can be in the graph, so in however way, so it comes. So, we will just pick up the paths, and then these are remember vertex disjoint things, so they do not share any vertices. So, now what is important for us is this last vertices, this is the last vertices, these vertices which are marked here. Now, these vertices are called the terminal vertices of the path cover P. terminal vertices. This is the terminal vertices of the path cover. Now, you see the cardinality of the terminal vertex will be equal to the cardinality of the path cover, because each path has one terminal vertex, and that is it. So, therefore, the path cover cardinality is essentially the terminal vertex, cardinality of the terminal vertex. Now, P is a minimal path cover if there exists no other path cover P dash such that terminal vertex of P dash is a proper subset of the terminal vertex of P. This is the condition. This is the condition. That subset condition is in the with respect to the terminal vertices. That means I will say that P is a minimal path cover if you cannot find any other path cover in G such that the set of terminal vertices of the second is a proper subset of the original one. For it to be a proper subset, it has to be smaller, and the path cover itself has to be smaller in cardinality. So, of course, the minimal path cover need not be a minimum path cover, but of course, it is very clear that if it is indeed a minimum path cover, it is a smallest cardinality set. It is a if it is a minimal path cover, right. If it is a minimum path cover, it has to be a minimal path cover. This is what we can clearly see. Now, let us look at a minimal path cover. So, let P be a minimal path cover. I will claim that I can get a independent set in such a way that every path in this path cover has a representative from the independent set. So, I will do it by induction. For small graphs, it is very easy to verify. For instance, a 1 node graph, 2 node graph, I will leave it to you to verify this the basis for the case of n equal to 1, n equal to 2, n being the number of vertices. Now, let us say for n minus 1 vertex graphs, it is true or more or below. Now, we consider a graph G with n vertices. Okay. Now, this n vertex graph, let us consider a minimal path cover of this n, any minimal path cover, let it be P, this is the P. So, let us say I am drawing this like this, so it can be anything. So, or I can just draw like this without marking the vertices, right. So, something is marked. Now, let us say I am interested in this is P1, this is P2, this is P3, like that. This is Pk, k number of paths are there, and the k paths are there in this path cover, suppose. And I am interested in the terminal vertices V1, V2, V3, of course Vk. So, of course, this is not an independent set. If it is an independent set, I am done, because this terminal vertex, this term of P, namely the V1 to Vk, is not an independent set in G. If it is, then I am done, because I already got a independent set with representatives from each path in the path cover. Now, let us say there is one edge here. So, in this thing, so without loss of generality, let us say the edge is like this. This is the edge, possible, quite possible. Any direction, let us say we can draw this like this. So, or in other words, we draw this edge first and then name it as y1, then v2, and the remaining as v3 to vk. Now, I decide to remove this vertex from the graph. This v1 will be cut away from the graph, and I will consider the remaining graph, this graph. Let this graph, new graph, the smaller graph be called G dash. In G dash, if I take this one, this one, this one, this one and this one, definitely it is a path cover of G dash. So, one question we can ask is it possible that this entirely disappeared in G dash or not, this portion? For instance, what if P1 was a single node path initially? Can P1 be a single node path in the original path cover? So, that means this portion was not there. So, that will never happen, because in that case we would have extended this path P2 to include V1, and so now the terminal set of this P2 to Pk, if you had looked, it will become V1, V2 is gone now, V1, V3 up to Vk, that will be a subset of the original terminal set. So, how can the original one can be minimal, right? So, therefore, that will never happen. So, there will be something here, let us call this vertex, this new terminal vertex V as V. So, this is maybe I can use it as V, right. Now, the suppose this P1, still I can say that this new path cover is P1 dash, because this is coming from P1. So, essentially after cutting this V1, I got P1 dash. This P1 dash, P2, P3, Pk, possibly that is indeed a path cover of G, but that need not be a minimal path cover. Suppose it is a minimal path cover. Suppose it is a minimal path cover of G. If it is a minimal path cover of G, then clearly I will get, by induction assumption, I will get an independent set in G dash, minimal path cover of G dash I mean. So, I will get a independent set in G dash such that some vertex of the independent set is present in each of the path, maybe something like this I will get, right, something like this I will be able to get some independent set. So, this red marked vertices will be the independent set. Well, so if it so happens that this P1 dash, P2, P3 up to Pk is indeed a minimal path cover of G dash, but that need not happen. Why it need not be a minimal path cover? It may be a path cover, but need not be a minimal path cover. Then what will we do? Then what will we do? So, the idea is to somehow prove that this is indeed a minimal path cover. It is not possible that it is not a minimal path cover, right. So, suppose it is not a minimal path cover, then there is some other path cover. So, there is some other path cover P double dash, right, and this P double dash, let me draw this vaguely, this original path cover, this original picture I will draw here with red color. So, remember this was the vertex V we cut, right, here there was this edge was there, because originally this was the P1 path, this was the P1 path, and then this was the edge we assumed to be there from, this is V1, this is V2 and this is V for that matter, this one was V3, V4 up to Vk. So, these connections are, so this is ending, these are the terminal vertices of those paths, and our vertex the graph G dash was like this. Remember this was the graph G dash, okay. V dash was like this. Now, our this is V, sorry, this is V, this is V1. Now, we are saying that this is not a minimal path cover. Why is it not a minimal path cover? Because there is another path cover. So, let us draw it like this. So, there is some other path cover, something like this, right, such that it somehow it ends in this terminal vertices only, somehow it will always end in this terminal vertices only, right. So, I am just drawing in some different way. So, this will take the same vertices, but in some different way they will, but then their terminal vertex of this new path cover, terminal vertex of this new path cover P double dash has to be a subset of proper subset of the terminal vertex of P dash. This is the problem. Now we will our analysis will be as far as this green path cover, that means P double dash, its terminal vertex set, can it contain this vertex V? It should be from here. So, suppose it contains V, this one contains V, then what will I do? I would simply add, I have this edge, right, add V1 to that. I will extend that path to include V1 also, and that P dash can be extended to become a path cover of original graph G. And now the P dash terminal vertices are this and this one, and this one is now gone and this is added. So, the all other terminal vertices are from this collection only, and then essentially the terminal vertices of this extended path cover will be from this. And naturally there was, because it is a proper set originally, something should be missing also. So, the original path cover P was not a minimal path cover for G, that is why. So, the original graph G's path cover itself was not minimal in that case. Again I repeat, if our P double dash, the supposed the path cover whose terminal set is a proper set of the proper subset of the terminal set of P dash, if the terminal set of P double dash contains this vertex V, in that case I can extend the path of P double dash which ends in V to include V1 also, because there is a direct edge from V to V1. And now we get a path cover for the original graph G, which is essentially that P double dash with this simple extension of one path. And naturally the number of paths here is strictly less than the number of paths in the original one. As we can see, this is a proper subset here, so naturally. And also the terminal set vertices of that path cover is a proper subset of the terminal vertices of the original one, namely V1, V2, V3, V4, because the only one which was outside was V, but that now instead of V we have V1 as the terminal vertex. So, naturally the minimality of the original path cover P is violated. So, it so happens that V cannot be there in the terminal set of P double dash. Now, we ask, then V is not there, can V2 be there? Same argument, if V2 is there, that particular path which ends in V2 can be extended to include V1 also, and then we will get a path cover of the original graph G. Now, you can see the terminal set has to be again a subset of the original V1, V2, V3, V4, that means the terminal set of P. And how can the original path cover P be a minimal path cover then? The same contradiction comes. So, V2 also cannot be a vertex in the terminal set of P dash. Now, this and this V and V2 are not part of P double dash. Now, essentially the terminal set of P dash can only take from V3, V4 up to Vk, which means the cardinality of P double dash is only k minus 2 or less, right, because only you see only at most k minus 2 terminal vertices there. So, it cannot be, the cardinality of the path cover itself cannot be more than k minus 2, right. So, now what I would do is I could simply add V1 as a singleton path along with this path cover P double dash, and that will make a path cover for the original graph G. So, now we get a path cover, new path cover of for the original graph, where the terminal vertices are this up to this plus V1. This is definitely a subset of the original terminal set V1, V2, V3, V4, V2 is missing there, maybe something else also is missing. So, it is indeed a subset. So, we have a smaller path cover than P with the terminal set of it being a proper subset of the original one, which is a contradiction. So, because the original path cover P was supposed to be a minimal path cover, so we got a contradiction. So, it is not possible that our P dash is not a minimal path cover, it has to be a minimal path cover then. So, if it is a minimal path cover, by induction hypothesis we know that there is a independent set in G dash itself with one representative vertex in each of the path of the path cover. So, we got the necessary independent set, and that same independent set will work for the G also. So, therefore, we complete the proof. So, this is why the Gallai Milgram theorem is true. Essentially, we can say that any if you take the cardinality of the minimum directed path cover in a directed graph, that has to be less than equal to the alpha of G, independence number of G. So, we conclude the Gallai Milgram theorem with that. Now, we will just quickly explain an application of Gallai Milgram theorem to the partially ordered sets. So, we have you have learned what relations are, and you know what equivalence relations are, the so called symmetric, transitive and reflexive relations. Similarly, there is this partial orders which are reflexive and transitive and antisymmetric. That means, if A and B are related, B, A are not related. So, if A is related to B, B will not be related to A, right, unless A equal to B. So, these partial orders are so an interesting topic, and look at this question. Suppose we are interested in covering all the vertices of a partial order in some way. So, let us say we consider a sequence of members of the partial order A, B, C, D, E, F like that, such that A is related to B and B is related to C, C is related to D, D is related to E, is related to F like that, right, or maybe A, B element of the relation and then B, C element of the relation like that, a sequence, right. So, in a directed graph notation we will have A to B, B to C edges, because AB is represented, the AB pair is represented by an edge here, the directed edge here. So, BC pair is represented by a directed edge from B to C, CD pair is represented from a directed edge from C to D, and so on. So, this kind of a sequence is called a chain. So, essentially it is a total order, a partial, a subset of the partial order. So, where the induced relation gives us a total order. Total order means every two elements are comparable or they are related, either one of. So, if A and B are in this set, then either A less than equal to B or B less than equal to A. So, A is related to B or B is related, now not both. So, this such kind of a subset is called a chain, a total order. Now, similarly, there is something called an anti-chain. So, anti-chain is a subset of the partial order where there is no two are related with each other. If I take A and B, neither A related to B in R, B related to A in R. So, you get the biggest such collection, that is the maximum anti-chain. It is equivalent independent set in our this thing. So, for instance, one way of easily visualizing this is to draw the partial order. See, partial order has a base element set of elements, say P, right, and then there is a relation, say usually put like this, right. So, the things, the elements of P can be seen as the vertices. So, vertices, and then the relation, if at all two elements are related, I can put an edge between them, and the way depending on the pair I can put an edge. You will never see the edge, there won't be a conflict, only one direction you will have because of the anti-symmetry, right. If A is related to B, I will put this thing, B won't be related to A. AB is a pair in the relation, then BA won't be a pair in the relation. So, therefore, so we can draw a directed graph such that each edge gets exactly between any pair, there is only one direction, right. So, there is one direction. So, we will get a directed graph from the partial order that way. So, you may, if anybody is not understanding what this partial order thing is, I will advise you to just refresh your 12th standard material on partial order. So, you can, it is not much, not very difficult to pick up that. So, you do not need that much either. So, what we are interested in now is this question. I want to cover the elements of the partial order with the minimum number of chains. How will a chain look like here? So, the chain will look like, so, you know, A, say A is related to B, B is related to C, C is related to D, D is related to E, like that. I will get a directed path starting from A to B to C to D to E to, like that. So, I want to cover the elements of the partial order with the minimum number of chains. Then there is a famous theorem says that this minimum number of chains to cover a partial order is actually equals to the maximum cardinality of a anti-chain in the partial order. Cardinality of an anti-chain in the partial order. This is called Dilworth's theorem. Dilworth's theorem. Maybe we can look at this. See, every finitely partially ordered set, the minimum number of chains with union P, that means the union of the members of this chain, elements of this chain, is equal to P. That is equal to the maximum cardinality of an anti-chain in P, the biggest. And as we can easily see, the maximum anti-chain or any anti-chain for that matter is going to be an independent set, because for any pair we are not supposed to have either of these directions. So, that means there should not be an edge in that, an edge. So, that means anti-chain correspond to an independent set in the corresponding directed graph. So, what we see is because no two vertex in an anti-chain can be in the same chain. So, we definitely need at least as many chains as the number of elements in the anti-chain. So, like this is equivalent to saying that see the number of chains, number of, so the cardinality of the anti-chain, biggest anti-chain, the cardinality of the maximum anti-chain should be a lower bound for the minimum number of chains required to cover the partial order, right, cover the elements of cover P. But the other way, that means actually this minimum number of chains to cover the partial order is the minimum directed path covering the corresponding directed graph, isn't it? Because if you take a chain, it is a directed path, you are covering all the things and they are disjoint. Therefore, it is indeed a minimum directed path cover. So, we know by Galle Milgram theorem that the number of minimum directed path cover cardinality is less than equal to the alpha. So, essentially this will be So, you can say less than equal to also. So, therefore, this will become equality. The cardinality of the maximum anti-chain is alpha, remember, right, with respect to the graph, and this will become MDPC of G, right. You know that this has to be greater than this. That this is less than this follows immediately from the definition, because any anti-chain, two vertices in the two elements in the anti-chain cannot be part of the same chain, right. So, therefore, we can understand that both inequalities are, this is less than equal to this and this is less than equal to this. From that we can infer that both are same. The Dilworth theorem says that the minimum number of chains required to cover the partial order is equal to the maximum cardinality of an anti-chain in the partial order. So, it follows. So, now that is Dilworth's theorem. So, in this class what I have done is the proof of Galle Milgram's theorem, essentially which says the cardinality of the minimum directed path cover is less than equal to the cardinality of the biggest independent set in it. And then we use this to show Dilworth's theorem. This will immediately imply one side of the Dilworth theorem, the other side is trivial. Therefore, there it becomes equality, because the partial order will give us a kind of graph, directed graph corresponding to the elements of the partial order. We have the vertices, and corresponding to the directed edges we have, so essentially corresponding to the pairs in the relation, we have the directed edges. This graph, in this graph the chains correspond to directed paths. So, minimum number of chains to cover is essentially the minimum directed path cover, and the anti-chains, maximum anti-chain is equal to alpha. So, that becomes equal in this particular type of directed graph. So, we will, in the next class we will mention a little bit about the kind of undirected graph that we will obtain if you remove the direction from this kind of graphs. So, they are called comparability graphs, that I will briefly mention in the next lecture. Thank you.